Welcome to the last session of unit number 2, which is bipolar junction transistor and its biasing of the subject basic electronics. In this session, I'm going to explain the last theory, which is thermal runaway. And afterwards, we will try to solve few numericals to understand the biasing concept more clearly. So let us first of all understand what is thermal runaway. Thermal runaway. So it is one kind of phenomena which is related to temperature, and from the second term, that is runaway, we can understand it. It is a kind of a continuous process. Maximum power transistor can dissipate without any kind of damage. That totally depends on the maximum temperature which is handled by this collector base junction, right? So rise in the temperature across this collector base junction, that is due to cumulative internal heating process. So what is this cumulative internal heating process that I'm going to explain in the next slide, right? But before that, let us understand the output current of this transistor. When the transistor is in the common emitter configuration, then the output current is the collector current. So collector current in this transistor is expressed by this equation, which is IC is equal to beta times IB plus ICEO. From this equation, we can say that the output current depends on the magnitude of base current, right? So let us understand this cumulative internal process. For that, uh, we have to keep this equation in mind, that IC is equal to beta times IB plus ICEO, right? So if collector current increases, then the power dissipation at the collector base junction also increases, because power dissipation is directly related to the output current IC. So if output current increases, then the power dissipation obviously increases. And if the power dissipation increases, then this will give rise in the temperature at the collector base junction. So we can say that if collector current increases, that means there is increment in the temperature at the collector base junction because of this increment in the power dissipation. What happens if the temperature at the collector base junction increases? A transistor has the negative temperature coefficient of resistance. What does it mean? It means that increment, it means that increase in the temperature at collector base junction decreases the resistance, right? As the temperature increases, there is reduction in the resistance. The reduced resistance will increase the collector current, right? If there is decrement in the resistance, then obviously the current through that resistor increases, and that current is nothing but the IC. So IC will further increase, and because of that, power dissipation will also increase, and due to that, temperature at the collector base junction will also increase, and furthermore reduction will happen in the resistance, and because of that, collector current will further increase. So it is an ongoing process, right? It is an ongoing process. So this becomes cumulative process, which will finally results in damage or burning off to the transistor due to excessive internal heating. That internal heating is the rise in the temperature at the collector base junction. So this phenomena, this process is known as the thermal runaway, right? So this cycle, the result of this cycle is known as the thermal runaway. So how can we avoid this thermal runaway? So there are three ways. The first one is limiting collector current beyond a certain maximum rating level. So we should always keep watch. We should always keep track of the collector current, right? And we should not allow the collector current to go beyond a specific level. So in order to keep the power dissipation in the limit and ultimately to keep the temperature at the collector base junction within the limit, right? So second possible way to avoid the thermal runaway is the limiting power dissipation below the maximum permissible level. So that can be done by uh, keeping this collector current within the limit. And the third one is using the heat sink. If temperature increases at the collector base junction, then you have to provide a heat sink to the component so that whatever the temperature or whatever the heat is generated at the collector base junction, that will be taken to the ambient temperature via this heat sink. So you can prevent the transistor from getting damaged. So these are the possible ways by which we can avoid this thermal runaway. We can prevent the transistor from this excessive temperature parameter, right? So that is about thermal runaway. Now let us solve the first example. Uh, the statement is given that what is the collector emitter voltage for the transistor shown in the figure? Collector emitter voltage. So this is the collector terminal and here is the emitter terminal, right? Uh, the question says that the voltage between these two terminals, that is VCE. We are supposed to find out this VCE, voltage between collector and emitter terminal. And this is the voltage divider biasing circuit, and the transistor is in the common emitter configuration. So these resistors R1 and R2 form a voltage divider network. RC is the collector terminal resistor, and RE is the resistor in the resistor connected in the emitter terminal, right? So let us solve this example. Necessary values are given in the diagram itself, right? So we will take help of these values and we will find out the voltage drop between collector and emitter terminal, right? So what is the first step to find out VCE? So the first step is we need to derive voltage at the collector terminal as well as the voltage at the emitter terminal. So if we get VC and VE, then we can easily find out VCE, right? Because VCE is nothing but the VC minus VE. Voltage at this point minus voltage at this point is equal to voltage between these two terminals. So we are expected to first find out VC and VE individually. So let us begin with VE first. So to find out VE, the equation is VE is equal to VBB minus VBE, right? What is VBB? VBB is the voltage at the base terminal. So using that voltage divider concept, we can find out the VBB, and by applying the KVL at the input section, we can write VBB minus VBE minus this going from positive to negative, or voltage drop across RE resistor is the VE. So when we make VE as a subject of equation, we get VBB minus VBE, right? So to find VBB, as I said that R1 and R2, these two resistors form these voltage divider networks. So by using that concept, we can find out the voltage at the base terminal. So it is nothing but the R2 divided by R1 plus R2 into VCC. So R2 is equal to 2.2K and divided by 2.2 plus 10K into VCC. And when we substitute the values from this circuit diagram, we get VBB is equal to 1.8 volt, right? So we have VBB, we have VBE as well. Why? Because assuming VBE is equal to 0.7, actually it should be VBE, right? So there is a mistake over here. VBE is equal to 0.7. That means base emitter junction is in the forward bias condition. So the voltage drop across this forward biased junction is equal to 0.7. So we can assume that VBE is equal to 0.7. So we can substitute this VBB, that is 1.8, and VBE, which is 0.7. So we can get VE is equal to 1.1 volt, right? So this is one of the parameters we are expected to find out. Now let us move further to find out VC. So how to find out VC? So for that we have to apply KVL at the output section. That is VCC minus ICRC minus voltage at the collector terminal is VC is equal to 0, right? Once again, VCC minus ICRC minus VC is equal to 0. And in that equation, when we make VC as a subject of equation, we get VCC minus ICRC. What is VCC? VCC is given in the diagram 10 volt, right? But what about collector current? So collector current is almost same as the emitter current. What about emitter current? We don't have emitter current, so we have to find out emitter current. How can we find out emitter current? Emitter current is the current passes through this RE resistor, right? So in the previous slide, we have found out VE, voltage drop across this RE resistor, or voltage at the emitter terminal, both are same. So VE is equal to IE RE, and from that we can make IE as a subject of equation. So we can find out IE is equal to VE divided by RE. So in the previous slide, we got VE is equal to 1.1 and RE is given in the diagram as 1 kilo ohm. So we get IE is equal to 1.1 milliampere. And from that, collector current is also 1.1 milliampere because of this approximation, right? And so finally, we have value of VCC, which is from the circuit diagram. IC, that is calculated from this IE, and RC is also given in the diagram, which is 3.6. So when we substitute all the values in this equation, and when we solve for VC, we get VC is equal to 6.04 volt. And when we substitute VC and VE from the previous slide into this equation, we get voltage between collector and emitter terminal, which is 4.94 volt, and that is the answer of this example. So very simple. Now voltage divider biasing the circuit is given. Circuit parameters are also mentioned, like resistors and the VCC. And from these values and the circuit analysis we understood for this particular type of biasing circuit helps us to find out the unknown parameter, that is, in this example, VCE, voltage between collector and emitter terminal. Moving ahead, the next example is the find out ends of DC load line for the circuit shown in the figure. Also draw the DC load line for the given circuit, right? So ultimately, the meaning of these problem statement is to find out the DC load line. So how to find out the DC how to find out the ends of the DC load line. So from the theory perspective, you should remember two equations which are the 2 points of the DC load line on the output characteristic of this common emitter configuration, right? So output characteristic is between the two output parameters, output voltage VCE and output current IC. And this line is the DC load line. So in this problem, in this example, magnitude of this point and magnitude of this point we have to find out, right? So here you can see that point at this location is nothing but is VCC divided by RC, and the point at this location is nothing but the VCE is equal to VCC, right? So value of VCC is given in the diagram, that is 15 volt. So the one end of the DC load line is at positive 15 volt on the x-axis, and the second end is VCC divided by RC. So what is VCC? VCC is 15 and divided by RC, that is 3 kilo ohm, right? So the answer of that is equal to 5 milliampere. So which is on the x-axis here, IC maximum. So to answer this problem, we have to draw the characteristic, and for the characteristic, we don't need this IB is equal to 0, IB1, IB2, IB3, IB4 in this problem, right? We just need the y-axis, which is IC, x-axis, that is VCE, then draw a line. This point you have to mention as 15 volt, and at this point you have to write 5 milliampere. That's all. That will be the answer of this problem. And let us solve one more example, which is this one, right? So common emitter transistor is connected in common emitter configuration, and the problem statement says that calculate quiescent point for this circuit diagram, and take value of beta is equal to 100, right? Quiescent point means point on the load line, right, which intersect the IB curve on the output characteristic, IB curve on the output characteristic of the common emitter configuration. So this is the Q point, which lies on the load line and which is intersecting one of the base current curve. So we are supposed to find out the location of this point on the output characteristic. So to find out the quiescent point, you should remember that quiescent point is given as VCE Q, comma ICQ, right? That means we have to calculate these two parameters. The first one is VCQ and the second is the ICQ. And then we can look at this quiescent point, operating point on the DC load line. So how to find out this one? For ICQ, from the discussion of the biasing circuit, you must remember that for this type of biasing network, IC is equal to beta times IB, right? Beta times IB. That means I am following the reverse process, right? So that means if I want to find out IC, then what should I need? I need value of beta. I need the magnitude of base current. Beta is straight away given in the statement, which is 100. But what about IB? So to find out the IB, I have to apply KVL at the input section. that is over here, starting from this VBB going from negative to positive. So VBB minus IBRB minus VBE is equal to 0. So the equation will be like VBB minus IBRB minus VBE is equal to 0, right? So from that I can write IB is equal to VBB minus VBE divided by RB, right? That means IB is equal to VBB is equal to 15. Let us assume VB is equal to 0.7, and sorry, here it should be minus, and value of RB is equal to 500 K. So when we solve these for base current, we get IB is equal to 30 micro ampere, 30 micro ampere, right? Substitute this value of IB 30 microampere into this equation, and beta is equal to 100. We get IC, and that IC is equal to 3 milliampere. IC is equal to 3 milliampere. That is nothing but ICQ is equal to 3 milliampere. So one of the coordinates we have found out. Now let us proceed for the second coordinate, which is VCEQ, and for that we have to apply the KVL at the output section. So when we apply KVL at the output section, we get equation like uh, VCC, sorry, VCC minus ICRC minus VCE is equal to 0, right? Is equal to 0. Okay. So from these we can make VCE as a subject of equation. So VCE is equal to VCC minus IC and into RC. What is VCC? VCC is given in the circuit diagram, that is 15. What is IC? IC just we have found out, that is 3 milliampere. And what is RC? RC is also mentioned in the circuit diagram, which is 3 kilo ohm. So when we substitute all the values in this equation, we get the second coordinate of the operating point, uh, which is VCEQ is equal to 6 volt, right? So this is the answer for this example. ICQ is equal to 3 milliampere and VCQ is equal to 6 volt. That is the operating point, that is the Q point for this circuit. Okay, that's it for this session. Few examples, few numericals are given at the end of the chapter in the material. Try to solve those numericals, and if you find any difficulty while solving the example, you can approach me. Thank you very much.